Okay, I'm ready.
All right. Okay, welcome to this press conference today, this afternoon, with the latest news from the, I hope I can pronounce it correctly, the Eyjafjallajökull volcano in Iceland. And I believe Professor Schumann and Dr. Weinzierl from Munich will report about this. They just landed, I believe.
Yeah, on Monday.
The plane just landed on Monday with the latest measurements from above the volcano.
Yes, thank you very much for this chance to present this material to you. First of all, perhaps let us introduce ourselves. I think you see here the title page, and you see the names. I'm the director of the Institute of Atmospheric Physics of the German Aerospace Center, Deutsches Zentrum für Luft- und Raumfahrt, and my institute is in Oberpfaffenhofen. And this institute, with a large number of co-workers, which are not all listed here, performed measurements with the research aircraft of DLR Falcon over Europe during airspace closure. So since our first measurements took place April 19, and our last measurements took place last Monday, May 3. May 3. So that is the span while we were measuring. So we had the background, and perhaps you go, and let us stay there. The background is, of course, that European airspace was closed on Thursday the 15th, and in the evening. And of course, immediately, many scientists, including us, realized that this is something where we have, first of all, the chance to make new science and new investigations of interaction of aerosols and particles with the atmosphere. But also, of course, we, as an institute of the German Aerospace Center, have an obligation to support and to provide information of relevance for aviation. So we immediately started to prepare for measurements. The situation was not easy because the aircraft had been used the days before for another objective, was empty, free of instruments. The instruments had to be reconverted to this situation. Then on the Monday, April 19th, we were able to make our measurements. And perhaps we can show to you an overview slide. Let us start with the conclusions. The conclusions from our measurements were the following. We performed measurements with our research aircraft, the Falcon, between April 19 and May 3, 2010. On board of the Falcon, we had a LiDAR, which is a light detection and ranging instrument, like radar, but with 2 micrometer wavelengths laser light. And this pulse LiDAR observes the vertical structure of the atmosphere. In particular, it measures the backscattered light from the atmosphere, from aerosols and clouds in the atmosphere in general. We also had in situ aerosol measurements, and this in particular was set up and is being analyzed by Bernadett Weinzierl to the right of me, who, by the way, is also leading a young research team at the University of Munich and at DLR at the same time. And we had in situ measurements for trace gases, carbon monoxide, ozone, sulfur dioxide, water vapor, which is trace gas in the stratosphere at least, and also methodological parameters, wind, turbulence, position, speed, etc. The measurements were performed first over Leipzig. Why did we select Leipzig? We select Leipzig because there was a ground-based LiDAR looking upwards into the atmosphere. So we went to a place where a ground-based LiDAR was positioned and made measurements at the same place, went down vertically or spirals down with the aircraft and up again to make direct comparisons that can be used to calibrate LiDAR observations. Because a LiDAR sees the light that comes from a cloud, and the light which comes from a cloud is a complex function of the number of particles, the size of the particles, the composition of the particles, the shape of the particles. So all this information has to be known together, and our in situ measurements complemented the knowledge required to analyze LiDAR observations of the atmosphere. And in the end, to come up with the mass loading, the mass concentration, how much ash per volume is in the atmosphere. So the result of that measurements on the April 19th was that the mass loading in the layers over Leipzig was 60 micrograms per cubic meter with an uncertainty of a factor of 2. Could be a factor of 2 smaller, can be a factor of 2 larger. So that is the uncertainty range. And actually, it could be even, it's difficult. It's difficult measurements. So this value itself has considerable uncertainty, but the order of magnitude should be absolutely correct. And that was over Leipzig. It was in a volcano ash situation which was already aged. It was already 5 days old since the emission. And the situation there was comparable to Saharan dust situation. Typically less than 200 micrograms or 0.2 milligrams per cubic meter, where aviation normally goes through Saharan dust. And we ourselves, Bernadett, Weinzierl, and other team members had been within a German research project, SAMUM, over the Sahara in the recent years. Is that okay? Do you have any comments? No. Okay. That was the first very important measurement, and this had big impact on the operation of aviation at that time. In fact, the German ministry was asking us whether we could fly, and the German Weather Service and the Volcanic Ash Assessment Center in London, they were all looking forward to see these results in order to assess the situation with respect to aviation over Europe. And now, after we have all the information, also with respect to thresholds of what kind of loading in the atmosphere would be acceptable for aviation, now we can say that at that time, from Monday at least, on April 19th, one could have flown over mid-Europe. But the knowledge at that time was not the same as we have it now. So, and what I also can say, also in the looking backwards, that on Saturday, April 17th, it was a reasonable decision not to fly. The loading was definitely too high for normal operation at that time. Okay, this was the first part of the story. We then made measurements which I don't want to explain so much, but then we got a call from the people who were responsible for transport in Iceland, and they asked us whether we could come to Reykjavik and could measure the ash loading over Reykjavik, because they had the impression that the warning was covering a too wide area. They were hindered in flying, and they thought that is not justified. So they asked us to come and to see whether it's justified. And of course, we had immediately the interest to fly in order to detect whether we can measure the mass flux of how much ash really comes out of the volcano. And that was the idea why we wanted to fly. And I think then perhaps Bernadett Weinzierl should now report a little bit about what we have observed that flying over the volcano in Iceland herself.
Yeah, so we did several flights over the volcano on May 1st. No, we arrived on the 29th of April. And at this time, the volcano was not very active. We could only see a white cloud. And then we did a measurement flight 2 days later, and it was really interesting because at that time the volcano was blowing up a lot of ash, and we could really see a dark ash plume stretching more than 200 kilometers away from the coast. And the ash loading was so high that we decided not to fly into the ash cloud, so we flew several times with the LiDAR over the cloud and measured the wind speed in the ash plume and the thickness and the length and all those parameters. And one day later, we decided to fly a little bit further away from Iceland. So on our way back to Scotland, we probed the ash plumes about 500 kilometers away from the source. First we flew over the plume with the LiDAR, and then we saw how thick it is and where the upper top of the plume was. And then we descended 300 meters and crossed the plume and another 300 meters. And so we went down. And then we really got very high concentrations. And we decided to stay only 50 seconds in this very high plume. And then we left the plume and flew further away to Scotland. And it was quite impressive because you could smell the ash plume. It was a smell like sulfur and something else. And yeah, we got very nice measurements and it was quite impressive.
So I was very glad when I got a telephone call from her and the team, Oliver Reitebuch and others on board the aircraft, telling me that they arrived safely in Stornoway on the Hebrides, which is west of Scotland, in the North Atlantic, more or less. And so there was a safe landing. The inspection of the engines and the aircraft showed no problems with the aircraft. There was boroscopy on the engines performed next morning, and they showed that the engines in the aircraft were without a trace from the volcanic ash. So the aircraft was ready to leave again the next day from Stornoway home to Oberpfaffenhofen, which is a special airport near Munich in southern Germany. And this actually, we designed this measurement such that we took the time when the Falcon was over the Iceland volcano and then used trajectory modeling with weather information to compute where the plume would be the next day. And then we measured at the place which was predicted to be the same ash mass again as we had observed over the volcano itself. So it was a Lagrangian experiment. One day after the first measurements, we were in the same air mass the second time. And then the air mass went on to Scotland and first to Ireland. And in Ireland, there was again a closure of the airspace on Monday because of that plume, which we had been measuring in. And the same plume was measured locally there by our partners at Mace Head in Ireland. And then a day later, the same air mass, which then was over Scotland, was traced by our British colleagues with another aircraft with other measurements at the same place. So now we have an observation over 4 days, or 3 days with the first, second, third, and fourth case, where we have observation of one and the same volcanic ash situation, which is, of course, an ideal situation to check modeling and to understand what happens with the ash. So what we found is from the data we can deduce a very first and very still rough estimate, because it's just 2 days ago, please take into account of that, of the mass in terms of kilograms per second of ash emitted from the volcano. And what we measure is the width of the plume, the depth of the plume, the speed of the wind, and the ash loading at the place where the Falcon was in the plume. This is very likely not the maximum concentration, because the maximum concentration is very likely lower down within the center of the plume where we have not been. So what we compute is the lower bound. We cannot have the maximum. And the lower bound itself has uncertainties, because to deduce the mass loading from the measurement methods which we have has many uncertainties. I already listed refraction index of light, mass density, and many other parameters that we need to know. So there's at least a factor of 3, I would say, of uncertainty to the number which I now give to you. Actually, is 3,000 kilograms per second of ash that comes out of the volcano, and it is still there in the plume after 7 hours age. Certainly there was more at the beginning. Much already fell down in the first minutes. Yeah? In the second, there are big stones initially and other material. They are not measured. We measure the mass that arrives after 7 hours in the plume. And even that is only a lower bound. The actual value will be higher We can't know it better than this way. Okay. We also got information about the particle sizes, and we got information about the air composition. As you had already heard, Bernadett was smelling the sulfur dioxide, and the measurements which we had on board show us that it was as high as we had it in the very darkest days in cities in East Germany, when there was very high sulfur dioxide loading. Then again, you could smell it. But that's comparable. So it was not dramatic, not a factor of 10 or 100 more than that. It was of that order. But it's a lot. It was about at least 10 times more than the maximum that was observed over Germany the days before. Yeah. Now, I think this has scientific and operational consequences. The data will be used to calibrate prediction models so that in the future we will have more reliable predictions of volcanic ash loads. Also, we have learned that only by a combination of modeling, LiDAR observations from ground and from space and from aircraft, plus satellite information, plus in situ observation, you get a sufficiently complete picture of what the situation really is. And we also have demonstrated that there's a need for an improved linking between operations, weather services, etc., and academia. I'm myself in a good situation because I was a member of the scientific board of the German Weather Service. We have a long-standing, intense cooperation with the German Weather Service. We know all people there. So there was easy communication with them. But the rest of the world had very less access to operations. So valuable information was available all over Europe, but not inside the operational system at the same time. So these linkages have to be improved. And I think it's obvious that one needs for the future such an aircraft as we have it, the Falcon, which goes up to 12 kilometer altitude, 3,500 kilometer distance, has had 3 or could have 5 scientists on board, has about 1,000 kilograms of instruments to be carried quickly with jet speed to any place over mid-Europe, and with a landing in between. We landed in Edinburgh. With one stop over in Edinburgh, we went to Reykjavik, or Keflavik. So we need such an emergency aircraft besides the aircraft Harlow that we are now preparing for high altitude and long range research in the atmosphere. So this is, I think, the conclusion and the main story. And I could have shown many pictures, but that's just, I will give a presentation on this. We will give together a presentation on this tomorrow evening here at this conference.
Okay, thank you very much, Professor Schumann and Dr. Weinzierl. Are there any questions from the room?
Hello, Chris Schrader with Süddeutsche Zeitung. You said that, looking back through your data, you would say that until Saturday it was justified to have a flight, stop flights.
Yeah, absolutely.
And I don't know where exactly you got that conclusion from, because your measurement started on 2 days later.
Okay, yeah, I said it's a retrospective view. It's not based on the information which I had on that Saturday. On that Saturday, we had observations from LiDAR, from ground. My institute is in a personal union cooperation with the Institute for Meteorology at the University of Munich, LMU. And I'm myself an extraordinary professor at the University of Munich. So we have an intense cooperation with the university, and they operate a ground-based LiDAR, the so-called MULIS, M-U-L-I-S, operated by the Ludwig-Maximilian University in Munich. That LiDAR is an upward-looking LiDAR, from the ground looking upward. And they were observing the ash layer. And I could see it from my home laptop in my private home in the morning, very early morning on Saturday, because on Friday evening I returned by train from Bremen. Saturday morning, I could see how the loading was. I could see that the volcano ash was in about 4 to 5 kilometers initially, was about 1 kilometer thick. And I got telephone calls and information from Payerne in Geneva. It was just arriving in Geneva during Saturday morning. And then I could follow during the day how this plume was, the layer was sinking. And in the afternoon and the evening, the plume was in the boundary layer and was drawn away. So on the Saturday evening, mid-Europe was free in the airspace, it's say above 2 or 3 kilometers of volcanic ash. It was only at the ground, near the ground at that time. And the concentration was already diluted. It was spread over from Paris to the Black Sea. And it was over a huge area distributed, which has a consequence that it is strongly diluted, the concentrations went below. And all big particles, they are falling down. A particle of, how much, say, 100 meters diameter falls within a day from 10 kilometers to the ground. So all the big particles must have been gone at that time. So only very small particles remained in the atmosphere. The problem was I had this impression, not in the final conclusion as I tell it to you today, but there was obvious to me that it was an exaggerated situation not to fly, and I was calling the responsible people. I had direct telephone communication with the Ministry of Transport in Germany, not with the top minister, but with his co-workers. And I told them that to my impression, the airspace is free at above 2 or 3 kilometer altitude. And then, of course, it was obvious there were no accepted threshold limits when aviation can fly in such a condition. The rules and the law until recently is and was, you are not to fly in an air mass that contains volcanic ash, dot. Without more quantification of what that means, because some ash is always anywhere. Yeah. And so there were no thresholds. So they had no basis to make a decision. I mean, a person who is not educated in understanding a LiDAR picture had no potential to decide himself to take over the responsibility to say, yes, we can fly. Because the laws and the rules, to which also the industry was contributing, of course, was not ready at that time. In the last week now, suddenly we now have these thresholds. Yeah? So now, having known the thresholds before, 1 week earlier, then one could have decided. So that is the situation.
More questions?
Luc André from AFP. You flew through these volcano ashes and your plane was in a good condition. So do you understand the critics from the air companies saying we can fly in too? And they made test flights to prove it's okay.
I mean, those who are criticizing are responsible themselves. The airlines, the engine industry, none of them really made sure that they know what are the limits to be allowed to fly. And that is so those who criticize should first look to behind their own door. And actually, it's the International Civil Aviation Organization, and we are all members of this organization, more or less directly, had discussed this earlier this year. There was an international conference, and they came not to an accepted threshold. And I understand this. It's very difficult to give such a threshold, because the threshold is engine dependent, is aircraft dependent. If you give one number, it's a high risk. Each engine is different. There are different pores and holes in various places, and they behave differently. So to give one fixed threshold for the whole aviation fleet is justified only if you are sufficiently far away from really dangerous situations. And what the industry tells me, because I was in direct communication with many of these people, actually also in an expert meeting at the ministry in Berlin on that, I understand that previous aircraft were flying through volcanic ash clouds with a mass concentration which was nearly a factor of 1,000 higher than what we now have as a threshold. 1 gram per cubic meter, not 1 milligram per cubic meter. So, and then they had engine problems. But this is really far higher than the threshold which is given now. But still, I must confess, I asked for that also in these expert rounds. Where is the evidence? Where can I check whether the threshold is really well justified by evidence or not? I have not seen the evidence yet.
But the closure, Holger Kocher, freelance from Germany, the closure of the Irish aerospace a few days ago was, considering these thresholds, justified.
I will show you one photo at least. I mean, weiter unten. Sind wir auf Ihrem Rechner? Ja. Yeah, this one, for example. Can you see that? I mean, this is the ash cloud leaving Iceland, yeah? I think you would not like to fly through it, how would you?
This is Iceland. What is it about over Ireland?
Yeah, it was at the place which was midway between Foto oder? Ja, das war dann, ja genau, das ist dies hier, ne? This, perhaps you explain.
So this is a picture taken about 15 minutes before we flew into these clouds. And as you can see here, it's really hard to decide if it's a cloud or if it's an ash cloud or if it's something else. And if you don't have instruments which tell you that you are in a cloud, you wouldn't see it. So.
But even in here, you get an impression. I think this. Could you say where you think it was?
So I think this
black part, you know.
This.
Yeah, that's how it works.
This gray black part here is the cloud, and
you see some darkness here at the horizon, but you see it's not obvious for an eye, and from the measurements, we know it's dramatically high.
Yeah. So we were only 50 seconds in this cloud.
And that was enough. Yeah.
Randy Shostak, reporter with EOS, the newspaper of the American Geophysical Union. A couple of joint questions. If there couldn't be an agreement on the threshold at the recent conference that you were at, how did the threshold limits then come about so quickly?
Okay.
And are these thresholds widely agreed to? And can you elaborate on whether and why you believe the threshold is valid?
The threshold was set up in international conferences organized by telephone conferences from the Civil Aviation Authority in UK. And participants of that conference were the whole aviation experts in the world, from airliners, from engine industry, from aircraft manufacturers, from operators, from certification institutions. Whoever has to say something on that was involved in it. With about 100 people in the telephone conferences. And there, of course, there was a smaller team preparing papers and drafting the thresholds and the rules, how to apply them. And then it was asked around, has anybody objections against this or has anybody support for this? And I heard about this, but I was partly, for some minutes at least, also for half an hour on this telephone conference, but it was too long for me because I had to make operations. And then the day later, I was also in the ministry in Germany where the German representatives from that team were together. So from engine industry and from the certification agencies, etc. And they cited that. And then it was really my role to ask, what is the evidence for that? And then, after I asked, in the presence of Minister Ramsauer, the industry explained in detail how they come to that. And they come to that with an immense effort. The last 10 days was immense industry effort on that. It was not just a desk decision. Rather than hundreds of technicians and engineers were collecting material on past reports of flights through volcanic ash clouds from various aircraft, airliners, etc., and past reports about observed damage or non-damage on engines, and collected that and assessed it as a whole picture. And they tell me that, for example, this aircraft near Indonesia, which flew and had problems with engine blowout, that was, from their assessment, a very high loading, But I must assess that's an oral evidence for me. I haven't seen the data myself, so I would like to see the data myself also. But from the presentation, I got the impression that this is a responsible assessment. So I had the feeling it was that we were in good hands there. So that means the 200 micrograms, which is a lower limit, is the same limit on which is the average Sahara dust loading in Saudi Arabia. In Saudi Arabia, every day you have dust loading, and on average over the year, the Saharan dust loading is near 200 micrograms per cubic meter. And that's normal aviation. Aviation goes through that every day. And of course, they need to inspect the engines, etc., what happens perhaps a little bit more often than in other places, but that's normal operation, up to 200 micrograms per cubic meter. The 2 milligrams, so it's 2,000 micrograms, so the 2 milligrams per cubic meter threshold is a difficult assessment. The assessment is it is sufficiently far away from the very critical values. It's sufficiently below. Whether it's 2 or 1 or 5 or 10, people are discussing still about. You know? But the 2 is just a practical criteria, because if you take 2, then the assessment is probably you could have flown all the time.
Could you tell us a little bit more about this aging of the cloud? You said you flew through it 4 times, 2 times yourself, and then the Irish and the English colleagues, I think.
Yes.
So is that correct? You were there day 1 and day 2, and day 3 was the Irish and day 4 with the
Colin Doyle, and then on the day thereafter, my British colleagues. Lee is the second name. I forgot the first name because I don't know her personally. She is the mission scientist. I have it on my computer, but so I know the name. She is the mission scientist on the aircraft which flew yesterday, and I have seen a report. It's too early to grasp this completely, but the impression is that there's a steady or continuous decay in the concentrations and the loading, so that one can follow. The main point, and that will be also our main statement, I think, even after 7 hours, there is sufficient time that the large particles are sedimented out. Yeah. You have no longer millimeter particles or something like that. Yeah? You're far away from that. Yeah.
But it's still true that it are the small particles, less than 10 micrometers, are the dangerous ones to the turbines.
No, I think what is dangerous is probably, certainly there are mechanical problems and there are problems which have to do with melting of the material. Mechanical particles can close the pitot rotor, measuring the speed of the aircraft, which if that happens, that would be a disaster, as we know already from other experiences. So it certainly must be far smaller than the openings in the pitot rotor. Otherwise, it would close that. I guess that's in the order millimeter or so, of what the openings of the pitot rotor are. Then, of course, you can have window problems. The captain can't see it anymore. And then, but that was not the case anywhere here. We have not any trace. We could not find ash on the aircraft, not on the window. There was no visible trace for people looking. There's no ash on the window. So it was not, in that sense, comparable to these big accidents which had been observed before. Still, there's the mass, and the material can melt. As far, I'm not the volcanological expert, so I don't know the material properties well. But what I understand is of the order 1,000, 1,200 centigrade that it can melt. And that is a temperature which is below the maximum temperature in an engine. Actually, the modern engines have even higher temperatures than the older engines. So it melts there, and then it can coat the engine. There are holes in the turbine blades. The turbine blades have holes to let air go into it, to cool it. And if those holes get closed, that could be a disaster. But my impression right after now, I would say, we never had a loading which was so critical that this could really happen. Yeah. With very few spots, perhaps, yeah, on the world. There are certainly high spots on which air aviation should have been flying around, but that was well predicted also, yeah? I mean, the predictions were sufficiently well to guide aviation correctly.
All right. So no more. Yes.
So with your data, what will be improved in the models that are used to predict such phenomena?
That's the first impression also, as Andreas Stohl, my colleague from NILO, yesterday in the presentation here at the conference summarized, is that the model used, the so-called NAME model, N-A-M-E, which has to do with nuclear something, that NAME model performed well. If you compare it with other models, you don't get dramatically or drastically different results. So that is not the main problem. The main problem now is you want to predict the mass loading. If you don't want to predict that there is something, that's easy. But to predict the concentration in terms of grams per cubic meter, that's far more difficult in absolute values. Whether we are below the threshold or above the threshold is now a far more difficult question than just to say there is something. So now we have to predict this threshold, which is very difficult. And that depends on many details: sedimentation, washout. And in particular, we have clear indications that this plume is not a passive tracer situation. There is internal dynamics. There is heat release from water that is condensing. There is radiation interaction. So that's a very turbulent situation. And this very turbulent situation does not mean that the particles follow just trajectories. They get mixed. And so that you need to know that good enough to predict dispersion, to predict the mass concentration correctly.
And in the case of another eruption, how do you detect it right in time? Do you have to send out aircraft? Do you have to use satellite? Do you have to use LiDAR? What will you do?
Okay, if the volcano erupts tomorrow again, and nobody knows, or perhaps this evening or now, now we have this alert, and actually, unless the scientists are now here on the conference, there are about, I would say, of the order of 200, 300 scientists in Europe who are able to observe such an ash loading with LiDAR observations from ground. There's this early network. There are other networks of observations. There are also sun observations from which you get the optical depths. And if that information now, tomorrow, and next days would be fed into the prediction system far better than it was prepared 2 weeks ago. And now we would be able to give a fair assessment of the mass loading with some safety limits, of course, safety limits, so that the responsible agencies could make a good decision whether it would be acceptable to fly or not in the next days. It can happen that we have to close the airspace again because the loading could be high, but that will be justified, I'm absolutely sure.
Okay, if there are no more questions, I will check it on the internet. Maybe questions from the outside? No, there aren't.
Yeah, perhaps one note on my interest here. Certainly we have the interest to run our German Falcon research aircraft longer. The Falcon is now 36 years older. And actually it should have been replaced by the new research aircraft Harlow. Unfortunately, the licensing, the certification of the instruments to get the allowance to fly were very difficult. Now we got the certification for the Falcon within 2 hours. On the Harlow, we worked for that for 6 months, for the same decisions. And so it's a lot of bureaucracy, which was not active now. So within 2 hours, we got decisions. And this is an old aircraft now. It's very robust. We know how it works. We have a lot of experience with it. We have established instruments for that. And we hope it can just stay there over the next time and be ready to be flown. And of course, also used from time to time to be on a modern state. For example, one task that we think is necessary is to fly with the Falcon from one ground-based LiDAR station to the next ground-based LiDAR station to measure the particle concentrations also under clear Sahara dust conditions, for example, and to compare that with the LiDAR observations, so to calibrate the systems, for calibration of the LiDAR systems. You can cross-calibrate it if such an aircraft flies over all those places and does this every month or so, yeah? Or every half a year perhaps. Then you would have a good calibration, and that's something which you should do operationally.
All right. Thank you very much for your presentation. It was very interesting. Thank you.
Okay.